We are fortunate to have amidst us Professor Douglas Osheroff, Department of Physics, Stanford University, and Nobel Laureate in Physics, 1996. Professor Osheroff obtained his bachelor's degree from Caltech in 1967 and PhD degree from Cornell in 1973. In 1972, while still a Cornell graduate student of Professor David Lee, Professor Osheroff made a crucial observation that led to the discovery of the supposedly impossible superfluidity of helium-3. He was actually studying magnetism in helium-3, but because the magnetic equipment was required elsewhere, Professor Osheroff was detailed to test a new refrigeration device. He noted an unexpected blip in the cooling rate when the solid-liquid mixture fell to 2.6 millikelvins. He had, in fact, observed a phase transition. Further work revealed that the transition was from a normal fluid to superfluidity. For his work on superfluidity, Professor Osheroff was conferred the 1996 Nobel Prize in Physics with Professor Lee and Professor Richardson. These researchers at Cornell University were low-temperature specialists and had built their apparatus themselves. With it, they could produce such low temperatures that the sample was within a thousandth of a degree of absolute zero. Professor Lee and Professor Richardson were the senior researchers, while Professor Douglas Osheroff was a graduate student in the team. The Nobel Prize caps a long list of awards Professor Osheroff has received. A member of the National Academy of Sciences, he has won the Simon Memorial Prize, the Oliver Buckley Prize, and was named a MacArthur Fellow. Professor Osheroff also won a Walter J. Gores Award for Excellence in Teaching. Professor Osheroff has served on the Space Shuttle Columbia Investigation Panel. Professor Osheroff, in his lecture entitled How Advances in Science Are Made, describes how as a graduate student he was able to discover superfluidity in liquid helium-3 despite the fact that the best low temperature physicists of the day had searched for the superfluid state and failed to find it. I now invite Professor Osheroff to enlighten us with his inaugural address. Professor Osheroff, please.
This talk actually has three messages which I want to give to the audience, and I will discuss them. The first is shown here, and I tend to illustrate these messages with also pictures that I've taken. This is part of the Grand Canyon at sunset. And the first of these messages is that those discoveries that most change the way we think about nature cannot be anticipated, almost by definition. How then are such discoveries made, and are there research strategies that can substantially increase one's chances of making such a discovery? And of course, I must think that the answer to that is yes, or I wouldn't have put it up here right now. There, by the way, are many reasons why you wouldn't want to always follow these strategies. Let me illustrate this with a linked chain of discoveries and inventions, starting with this person here. This is one of my great heroes as a low-temperature physicist. He has to be one of my great heroes, Heikki Kamralionis, who was in a competition with Dewar at the end of the 19th century to see who could first liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won in, I think it was 1898, when he succeeded in liquefying hydrogen. But already, of course, man had found evidence for the existence of helium on the sun, and within a few years, Kamralionis was able to acquire enough helium that he could try to liquefy it. I think his first sample basically would fill a small party balloon. Ultimately, I think he had about 200 liters of helium gas, but it was very difficult to get at that time. Most of the helium that we use today comes from natural gas wells, and that was not clear that that was going to happen at the time that Kamralionis did his work. So Kamralionis succeeded in liquefying helium in 1908, and then he did with liquid helium exactly what Dewar had done with hydrogen. He pumped on the vapor above the liquid, causing more liquid to evaporate. The system cooled, and the idea was to see where liquid helium solidified. What Dewar had found was that liquid hydrogen exists under an atmosphere of pressure at a temperature of 23 Kelvin, and if you pump away the vapor, ultimately under its own vapor pressure, the hydrogen solidifies at a temperature of 14 Kelvin. So Kamralionis tried to do exactly the same thing, ultimately reaching a very low temperature of 1.04 degrees above absolute zero, but he was never able to make his helium solidify. I personally have cooled helium-3 to a temperature of 1/10,000th of a Kelvin, and it stays very happily in a liquid state. Now, the reasons for that have to do with quantum mechanics, which was just being invented at this time. So it would really have been impossible for Camerlenus to understand why the helium didn't solidify. But rather than giving up, which is essentially what Dewar had done when Camerlenus liquefied helium, Dewar sent Camerlenus a short note that said, "Dear Camerlenus, you win, I lose, Dewar." And then Dewar basically got out of low temperature science. But instead, Camerlenus now looked around for some other interesting question of the day that he could answer with this new refrigeration process that he developed. And people were arguing about what would happen to the conductivity of a pure metal as one cooled it toward absolute zero. One school of thought argued that as you removed the thermal energy, the lattice vibrations would go away, and so the mean free path of an electron, conduction electron in metal would increase, and so very gradually the electrical resistance would drop toward zero. The other argument was that at some temperature, the conduction electrons, which were free to roam around the interior of the metal, would recondense on the ions from which they'd come. The system would become completely neutral and all conductivity would cease. So Camerlenus obtained a very pure sample of mercury, which is a metal that's very easy to purify, and he gave it to his graduate student. I put his graduate student's name up here, Gilles Holz, because Camerlenus actually was not of the habit of putting his graduate students' names on his research papers. Thank God that was not true for my thesis advisor. So here's the data shown as these green points, and you can see, in fact, that the resistance plotted here 0 to 0.002 of an ohm, and from 4 Kelvin to 4.5 Kelvin. The resistance is dropping rather gradually, but then at a temperature of about 4.2 Kelvin, there was a discontinuous drop in the resistance to a value of less than 10 to the minus 5 ohms, which was the resolution of their equipment. And when Gilles Holz showed this to his mentor, Camerlenus was sure that a lead had fallen off the sample, and I suppose I would have thought the same thing. However, of course, these results were reproducible, and this was, in fact, the first observation of superconductivity. In 1913, Camerlenus received the Nobel Prize for his work, not specifically for discovering superconductivity, because people really had no idea what this unusual state of matter was about at that point, but for having created this liquefaction process and for studying the properties of matter near absolute zero. He was the first person to do that. So let us look at the research strategies that allowed this discovery to be made. First of all, is the best instrumentation available, and really he had a unique piece of apparatus. And in fact, for the next 15 years, if you wanted to study superconductivity, you had to come to Leiden University, to Camerlenus' laboratory. He was the only person that could reach the temperatures necessary to study superconductivity. Don't reinvent, borrow technologies that you can. Dewar had invented the Dewar flask in order to liquefy hydrogen, and Camerlenus was quite happy to borrow that technology. Look into an unexplored region of the landscape, and literally no one had looked at the properties of matter at these very, very low temperatures. Ironically, up to this point, people were only interested in the properties of the liquid cryogens themselves until Camerlenus did his work. And this is really a very important thing for graduate students in particular. After working for 2 years to find where liquid helium solidified, Camerlenus gave up. But he didn't really give up. He used that as an opportunity to try something new. And so almost immediately he made a truly major discovery in physics. So failure might be an invitation to try something new. And so, however, Camerlenus for the next 15 years, I'm sure, cycled his liquid cryogen through the temperature of 2.17 Kelvin, which of course is the temperature where liquid helium undergoes a superfluid transition temperature. Now, Camerlenus actually noted that it appeared that the liquid helium stopped boiling at a temperature of about 2 Kelvin but he never investigated what was really going on. Had he done that, he would have, in addition, made another major discovery in physics. So be aware of subtle, unexpected behavior. Don't dismiss it. Well, no one got a Nobel Prize specifically for discovering superfluidity in helium-4. People knew that there was a logarithmically divergent peak in the heat capacity at about 2.17 Kelvin, and people didn't really know a lot about the properties of helium below that. It was Peter Kapitsa in the bleak winter of 1937 in Moscow who measured the viscosity of superfluid helium and found it to be less than 1/1000th of a poise, hence the term superfluid. Peter Kapitsa basically did this work in 1937, did not receive the Nobel Prize until 1978 for this work, 43 years later. I actually met him. He was the first time he was able to get out of Russia after many, many, many years. He had actually gone back into Russia. He left Russia during, I guess, at the end of the revolution, and he'd gone back to visit his mother, I believe, in St. Petersburg, and he was told that he could either stay under house arrest for the rest of his life or they would build him a research laboratory. And so he opted for the second. Anyway, but Peter Kapitsa actually shared the Nobel Prize in 1978 with a very unusual colleague. This was what is called a split prize. So Kapitsa got actually half of the prize money, and the other half was shared by two of my ex-colleagues at Bell Laboratories, Arno Penzias and Robert Wilson, for their work in discovering the cosmic microwave background radiation. So let's look a little bit at that discovery, because it was, in fact, a serendipitous discovery. First of all, AT&T had been doing experiments on satellite telecommunications, the ill-fated ECHO satellite project. I don't know how many people here remember that. And then later Telstar. And when they were done with these experiments, they gave this piece of apparatus, this high-tech microwave receiver, to Penzias and Wilson to make the first absolute radio noise measurements. Now let me remind you that actually radio astrophysics had its birth at Bell Laboratories, and I think that's, yes. So this, you can't see him very well. This is Karl Jansky. He was an engineer at Bell Laboratories, and when AT&T started trying to communicate telephone signals over radio waves, they found that there was a lot of excess noise that they couldn't understand. So they assigned Karl Jansky the task of understanding where that noise came from. And so he had a directional antenna that looked at noise that was coming down. And what he found was, in fact, that over a 24-hour day, in fact, the noise would have a peak. But what he found was, under careful measurements, that peak tended to advance every day by about 4 minutes. And when people that knew something about astrophysics learned about that, it was very clear, in fact, that this was the signature of an extraterrestrial source, something that was not tied to the Earth's rotation around the sun. And so Jansky actually wanted to investigate the source of this noise, which is gas clouds in the Milky Way galaxy, but he was told by AT&T that there was nothing that they could do if this noise source was extraterrestrial, and so they reassigned him to a different project. And it turned out the person that actually found out was a ham radio operator, found out where that noise was coming from. But anyway, so it's probably partly because of their failure to let Jansky follow his nose that they actually helped Penzias and Wilson a lot. Now, I have to go back to this device here. This is a horn antenna, which has the advantage that it doesn't look at radio signals coming from terrestrial sources. But the real key to this thing is inside this little shed here. There was a traveling wave tube maser amplifier, cooled to a temperature of 4.2 Kelvin. And this thing had a very low noise temperature. That is to say, it added very little additional noise to the signal that it was amplifying. Now, the maser, of course, had been invented by this person. This is Charles Towns. When he was at Columbia University, this Jim Gordon was his graduate student and later had a very fruitful career at Bell Laboratories. But it wasn't, this device, this is the second maser. It's an ammonia maser, basically molecular beams apparatus. And this was not the technology that Penzias and Wilson used. That was actually developed by Nicholas Bloombergen at Harvard University. So basically using a doped ruby rod. Well, this is the first data, May 20th, 1964. And I think where I was at that time, I was a freshman at Caltech at that time. And so what happens here, this is strip chart recorder, so the paper's being pulled underneath the pen, which moves back and forth. And so this is the noise coming from the antenna pointing a specific position of the sky. And then they have a microwave switch, which allows them to compare that noise to the radio noise radiated by a black body at a temperature of 4.2 Kelvin. And so then they do some calibrations, and their conclusion was that even though they'd pointed the antenna in a place which was known to have no radio sources, they saw excess noise at the level of about 3.3 Kelvin. So then they went back and looked at their wonderful antenna again, and what they found when they went inside here was that the pigeons had been roosting inside, and there were a number of pigeon nests, no pigeons at that point. So they knocked down the nests and mopped up the pigeon droppings and soldered a few copper plates back in place. But nothing that they could do would make this excess noise go away. So one day, Arno Penzias was up at MIT talking to a Professor Burke there, and Burke said about this strange noise, which of course wasn't just in one place in the sky, it was seemed to be coming from everywhere. And so Burke said that Penzias should call up Robert Dickey at Princeton University, because he had someone in his group, a theorist named Peoples, who had this theory that as the universe expanded, when electrons and protons combined to form neutral hydrogen, the radiation that existed at that point decoupled from the matter, and as the universe expanded, that radiation would cool. And so the temperature of that radiation was supposed to be a few degrees Kelvin. Now, it's interesting that Robert Dickey had not made this discovery. And in fact, actually what happened was that Penzias then called up Robert Dickey, and Dickey asked him a bunch of questions about how they made their measurements and everything like that. And then he agreed that he and his group would come up to Crawford Hill, where this antenna was sitting, and they would look at their apparatus and look at their data. And then he hung up the phone, and there were a few people of his graduate students were in his office, and he turned to the graduate students and he said, "Gentlemen, we've been scooped." And one of the people actually was in that office at that time was David Wilkinson. Later, David Wilkinson and I served on a national committee to revitalize physics education. He told me the story. Well, you'll see that name come up again later. But basically, the question is, why was it that Penzias and Wilson were able to see this radiation when they weren't looking for it, whereas Robert Dickey was looking for it but couldn't see it? Well, Dickey's apparatus was based on conventional tube amplifiers with hot cathodes, and therefore there was a lot of noise. The integrated noise temperature of Dickey's apparatus was 2,000 Kelvin. The integrated noise temperature of Penzias and Wilson's was 19 Kelvin. So therein lies the problem. And in fact, if you look at the relevant research strategies, again, use the best technology available, that really made all the difference. Now keep in mind that this wasn't what Penzias and Wilson were looking for, but it really helps to have the best technology. Don't reinvent the wheel, borrow if possible, and most of this apparatus was borrowed, except that Penzias and Wilson made this very key addition, that is this microwave switch, which allowed them to make absolute measurements of radio noise. Without that, they couldn't have made the discovery they did. look into a region of parameter space that is unexplored, and again, they were pioneers, first people to make absolute radio noise measurements. And finally, and this is very important if you're an experimentalist, understand what your instrumentation is measuring. Too often today, people buy a piece of equipment and they put it in their apparatus and they have no idea, but this thing has got many microprocessors in it, and it is just sending radio noise down inside the apparatus, corrupting whatever data comes from the sample. So you really have to be very careful. There was a case where Adelberger, who's one of these people that's looking for a non-1 over r squared term in the gravitational field, found something that appeared to not go like 1 over r squared. And in the end, after wasting basically 2 years, they found that they had a Newport translator, and when the computer told it to move by 1 centimeter, it moved by 0.97 centimeters. That was all of the effect. That produced the effect that they thought was very exciting. So you really have to measure your instrumentation and understand and have confidence in your ability to understand. Otherwise, Penzias and Wilson could have simply said, well, okay, we've got 3 degrees of excess noise, we'll just subtract that from all of our measurements. Okay, well, this is now from COBE satellite project, and it shows that radiation is essentially a perfect black body with a temperature of 2.725 Kelvin with an uncertainty of 1,000th of a degree. This was quite a tour de force when the COBE satellite went up. But now, in fact, we have WMAP. Now, I actually left out a slide. But what this shows, and in fact what COBE showed as well, but with less resolution, is that the temperature of that radiation is not uniform over the sky. It has fluctuations, levels of a few millionths of a degree. And when it was first seen, I mean, it wasn't clear that it was actually real, but of course it was reproducible. And we now know that that radiation results from fluctuations in the density of the universe just at the point where the universe became neutral. And so this, in fact, really has been a boon, and I dare say that it has finally brought cosmologists and observational astrophysicists together almost for the first time. And so for their work on the COBE satellite, John Mather at Goddard Space Flight Center in Maryland and George Smoot at the Lawrence Berkeley National Laboratories shared the 2006 Nobel Prize for Physics. Up to this point, in fact, the CMBR, cosmic microwave background radiation, had been awarded 1/2 of a Nobel Prize. The other half went to Peter Kapitsa. And so I always like to think, wow, you know, helium-3 got more of a Nobel Prize than cosmic microwave background radiation, which certainly I think at some level is a more profound discovery, I think. Anyway, here's the second of these 3 messages now. By the way, the background is a very small piece of the Iguazu Falls, which I recommend you all go see at the border between Argentina and Brazil. Anyway, the process of advancing science often leads to inventions and technologies that directly benefit mankind. However, doing this the opposite way doesn't work. It is impossible to know from where an advance will come that might solve a particular problem facing mankind. And I will give you one example, and that is nuclear magnetic resonance. Now, of course, I've found a very good example. I, by the way, use nuclear magnetic resonance in most of my research. So NMR was invented in 1946 at the end of World War II by Felix Bloch at Stanford University and Ed Purcell at Harvard University. And the idea was really to understand the distribution of charge in atomic nuclei. So just 6 years later, these guys get the Nobel Prize. They go to Stockholm. I know exactly how this works. The press come up and they ask you to explain what it is that you've discovered. And of course, these people have no physics background. And so after a while, they give up, and then they ask the second question: what is it going to be good for? And so when asked that question, Felix Bloch replied, apparently, I've not seen this written down, but plenty of people at Stanford that I've talked to were around when Bloch got that prize. Anyway, he's supposed to have said damn little, because he felt this was basic research, this had nothing to do with applications. Ed Purcell, a slightly more thoughtful person, suggested that one might use NMR to calibrate magnetic fields. So now let's see what the visionaries that invented NMR missed. Well, within a few years, people were able to produce very homogeneous magnetic fields, and then when they looked at did nuclear magnetic resonance on organic molecules in solution, they found that the protons didn't all resonate at the same frequencies. There were very well-defined triplets and quadruplets with shifts of typically a few parts per million, and it very quickly became obvious that these were as a result of spin shifts and chemical shifts in the bonding of the atoms that make up these molecules. So at that point, NMR became an essential tool for organic chemists. And I think even today, it's difficult to go into an organic chemistry laboratory without seeing an NMR spectrometer. Well, later on, there actually Richard Ernst, who is Swiss, had come to California and was working for Varian Brothers in Palo Alto, very close to Stanford University. And Richard Ernst had this idea that rather than slowly sweeping the magnetic field or the frequency, what one should do is basically use a powerful RF pulse to tip all of the spins and then let them undergo free precession. And the frequency of each spin would be determined by the local magnetic field that it felt. And so then you sum all of these things up and you get what's called the free induction decay signal. You do the Fourier transform of that, and that gives you back the distribution of frequencies of all of these spins. And once that was done, in fact, he and another Swiss, Kurt Wuttrich, basically started doing very complicated pulse sequences where you, for instance, would tip, you measure the frequency of this proton, and then you would tip this proton and see how that changed the frequency of the other proton. And this basically is essentially called two-dimensional NMR, but it's two frequency dimensions, not two spatial dimensions. And so this ended up really, again, being a very powerful tool for chemists, not for physicists. And so in 1991, Richard Ernst won the Nobel Prize in Chemistry. So this is the second Nobel Prize for NMR. Now, it was interesting, the person he was working with, Kurt Wuttrich, who was the guy that was actually developing most of these fancy pulse sequences, didn't share the prize. And I know both of these guys, and I like both of them. And so I asked Kurt, I said, Kurt, how did you feel? You must have been disappointed when you didn't share the Nobel Prize with Richard Ernst. And he said, no, I wasn't disappointed. I was mad. So Kurt Wuttrich actually continued developing these very complicated pulse sequences, and ultimately he was able to determine the three-dimensional structure of even simple proteins. And this was important because you could do this in an aqueous solution. The only other way of getting this structural information was to crystallize these things and then do X-ray crystallography. And it wasn't very clear that, in fact, the structure of something as sensitive as a protein would be the same when in crystalline form as it would be if it was an aqueous solution. So I think it was 11 years after Richard Ernst received his Nobel Prize. Kurt Wuttrich, shown here, is receiving his Nobel Prize also in chemistry. So that's the third Nobel Prize for NMR. But even as all of this development was going on, a very separate but parallel development was going on, and that is the development of MRI. So people, I dare say I was one of the first people that did that, began to realize that if you applied a magnetic field gradient across your sample, then all the spins would have encoded in their frequencies the position where they were sitting. And so you'd get positional information, and if you then applied the magnetic field gradient in 3 different directions, you could get pictures. And this is, of course, most important for medical applications. Now this, I can tell you, I know, is a very healthy human need. I've had both of my knees MRI'd, and they ain't so pretty. So, so even I've actually benefited from this technology. And in 2003, 1 year after Kurt Butrick won his Nobel Prize for his contributions to the development of NMR, Paul Lauterbur and Peter Mansfield shared the Nobel Prize in physiology or medicine, the 4th Nobel Prize for physics. Certainly worth more than just calibrating magnetic fields. But I think we're not done yet, because in fact, Seiji Ogawa, who was working at AT&T Bell Laboratories in the biophysics department, and I think he was working with David Tank, who was the head of that department, and he was doing MRI on rats, live rats. And I think these are human brains rather than rats' brains. What he found was if you used a pulse sequence that was sensitive to the rate that the protons recover parallel to the magnetic field, you found that you would get very bright signals in certain places of the brain, and these were not the same places over and over again. What they found, of course, that what they were looking at was those places in the brain that were processing information, because they were then using oxygen, and they would change the oxygenation of the hemoglobin in the blood in that region, and so that's what they're looking at. Now this is really changing the way a lot of psychologists do their work now. Unfortunately, of course, you don't know what the brain is thinking, but you can get some idea as to what part of the brain is doing it, and of course the brain is partitioned so that various parts do different things. So I would predict that that might win a Nobel Prize. I'm hoping it will, actually, but that would be the 5th. Well, now one thing I learned in developing this talk was you don't want to say too much about the serendipitous discoveries that your friends have made, okay? So, because they may not look as brilliant in retrospect as you might have thought if you didn't know anything. And so I'm quite free to tell you about how clueless I was, but I'll also try to tell you why I went into low temperature physics in the first place, and so I'll try to be honest if I can. So let me first say a little bit about the history of helium-3, because it essentially is an isotope of helium that virtually almost doesn't exist on Earth anyway. It's a part in 10 to the 12th, or a few parts in 10 to the 12th of our atmosphere. And it was really, virtually all of the helium that I've ever studied was probably born inside a hydrogen bomb. Not one that was going off, of course, but hydrogen bombs require tritium as a generator of neutrons, and the tritium decays with a half-life of 12.4 years. So there was a guy at Los Alamos in 1948 when Los Alamos was trying to develop the hydrogen bomb named Ed Hamel, and his job was to keep the tritium sample clean. So every once in a while they would clean out this helium-3, and he saved the helium-3. He didn't throw it away. And then eventually he decided that they would actually cool this helium-3 sample down and find out what the vapor pressure was above helium-3 liquid. So they did that experiment in 1948. The results were published in 1949. Now, Ed Hamel did one thing that he probably shouldn't have done, and that is he actually published how large their tritium, their helium-3 sample was. Well, that, of course, told the Russians something about how large their tritium sample was. The Russians then started doing very similar experiments on helium-3, but they would never say how large their samples were. And when Ed Hamel was in his 80s, I did a telephone interview with him. I was giving a talk for the American Physical Society, and he said he figured that was the first really serious security leak from Los Alamos National Laboratory. Anyway, so helium-3 is interesting because helium-3 atoms are Fermi particles, like conduction, like electrons. no two can occupy the same quantum state. And so people were interested in seeing how far this parallel went, and through the 1950s and I guess into the 1960s, people were measuring the normal state properties of liquid helium-3 to ever and ever lower temperatures. And in 1957, of course, Bardeen, Cooper, and Schrieffer came up with their theory, which finally explained the superconducting state which Camerlionis had discovered. Took that long to do that. But within 2 years, people began to speculate that this theory, which was very, very specific for conduction electrons in metals, might be modified so that, in fact, that it would predict superfluidity, BCS superfluidity in liquid helium-3. And so the hunt was on. Of course, Phil Anderson, a good friend of mine, was one of the people that was guilty of predicting a transition temperature of 80 thousandths of a degree. They thought that was very low, but in fact, very quickly, within a few years, John Wheatley had actually cooled helium-3 under its own vapor pressure to 2 thousandths of a degree and didn't find any superfluidity. And so this was, I guess, just 2 years before I became a graduate student at Cornell, and by the time I did so, the common wisdom was that this superfluidity in helium-3 was a pipe dream by the theorists. And I suppose people in India know what pipe dreams are all about. I don't know. It's, what is it anyway? What do you smoke? Opium, I guess. Actually, that's probably more China, right? Okay, so pardon me. Anyway, so the reason I went into low temperature physics wasn't to discover superfluidity in helium-3. Everyone felt that it simply wouldn't exist. But rather, there were new refrigeration technologies being developed that gave the promise of allowing you to look at nature in a new and different realm. That is to say, you could, in addition to cooling it down, you could apply magnetic fields and do other things. So one was the helium-3, helium-4 dilution refrigerator. And when I was a first-year graduate student at Cornell, by the way, had, as near as I can tell, no course requirements for graduate students. So I actually built a helium-3, helium-4 dilution refrigerator as a first-year graduate student. Okay, went the wrong direction. So, but let me go back a little bit, because I think what any physicist or any scientist or any person does in his life, I think a lot of it has to do with early childhood. And I think if you want to stimulate people to go into science, you need to start at a very early age. So this is me. I was son number 2. My father was a medical doctor, but he had actually, during the Great Depression, had gotten a master's degree in chemistry, and then his father, who was a medical doctor, convinced him that it was probably smarter to seek out a career in medicine rather than in science. And I think my father kind of felt sad that he didn't become a scientist himself. And so he and I would do experiments together, and he would come home with junk from the telephone company and stuff like that, and I would learn ways of making this semi-lethal. So for instance, he came home with an ignition coil from a car. You put in 6 volts and you get out 600 volts. So I said, pardon me, 6 volts and you get out 2,000 volts. So I says, what happens if you put in 600 volts? So I had a bunch of paper capacitors from the telephone company, and I wired these things all up in parallel. And then I bought a diode tube and borrowed a transformer from my brother, who was a ham radio operator, charged these guys up to 600 volts, and then discharged that across the primary to this ignition coil. I could get sparks this long, and these things, I think, were literally lethal. But before I killed myself, I made the mistake of discharging the 600 volts across my body. And the next thing I knew, I woke up on the other side of the room. You get a violent contraction of your muscles when that happens, which is good because it throws you away from the offending charge. And I had no idea how long I'd been unconscious. But I never told my parents about that because high voltage electricity was just too fun. My senior year in high school, I borrowed my mother's car and went up to Seattle and kind of told 3 medical supply houses that I wanted to build an X-ray machine as a science project. Could they give me any stuff? And I came home with a carload of stuff. When I sorted it all out, there's not that much in an X-ray machine. And I had everything. I had a sort of good tube. I had a 100,000 volt transformer, and then auto transformers and all of the other things that you need. And so, you know, I always thought that if you didn't turn on the filament, you weren't generating X-rays. That's not a good, anyway. I irradiated myself pretty good. I would say, besides my father, the person that most influenced me was actually not my physics teacher, but my chemistry teacher. He had actually been a graduate student at Stanford, was married with kids, ran out of money, dropped out and became a high school chemistry teacher. But he actually would spend a couple, maybe 3 lectures or class periods during the year talking about what research was all about. And the way he described it is the way I still think of it today. And when I got my first major prize, which was the MacArthur Prize, I thought of William Hawke. And so I found out what his telephone number was, and I called him up. I was at Bell Laboratories in New Jersey. He was still in Los Angeles. And so I said, "Mr. Hawke, guess who?" And he says, "That has to be Douglas Osheroff." Now, this was 82 or something like that, and I'd had him as a teacher in 1962. How could he remember? I don't think he did, but he saw that I'd gotten this prize. I was completely dumbfounded. Anyway, so he was actually the advisor for our science club. This nerdy character, that's me, and all these other guys. A lot of them were my good friends in high school. I should say that amongst certain segments of the population, my main claim to fame is not the Nobel Prize, but the fact that I was classmates with Kurt Cobain's father. Okay, there you have it, Don Cobain. This is my helium-3, helium-4 dilution refrigerator, and this thing would reach a temperature of about 15 thousandths of a degree, so I got to go a bit faster. Then when I was at Caltech, of course, Feynman really influenced everyone, I think, in one of 2 ways. I think 40% of my freshman class didn't come back for their sophomore year. Those are the ones that weren't into Feynman physics, I suppose. But for those that were, it was an absolutely amazing, fantastic time. And when I was being offered a faculty position at Caltech, I insisted on talking to Feynman and thanking him for having taught the undergraduates, including myself. I got involved in research, and this is something which is very important, I think. Virtually all of the Stanford physics undergraduates, physics majors, get involved in research. I got involved in astrophysics research, and mine were the 3rd set of human eyes to see the center of the Milky Way galaxy in the infrared. So it was pretty exciting. What that means, of course, was a blip on a strip chart recorder. You don't actually see in the infrared. But it was exciting, and so when I applied to graduate study the next fall, I applied to places that had very good astrophysics programs. But then I had an epiphany. I started realizing that astrophysicists don't do experiments. You can't change the temperature of a star to see what happens. And because of what William Hawke had told me as a high school student, I desperately wanted to do experiments. So I changed my field from astrophysics to condensed matter physics. And I'm sure that I'm very happy that I did that. Anyway, so there were 2 technologies the first year I went to Cornell. One was the helium-3, helium-4 dilution refrigerator. The other was something that had been proposed way back in 1950 by Isaac Pomeranchuk. Pomeranchuk was a theorist who mainly studied high-temperature plasmas. But when the people at Los Alamos liquefied helium-3, he started thinking about the properties. And liquid helium-3 is a Fermi fluid, so if you saw Fermi degeneracy, then in fact the entropy of the liquid would drop linearly with temperature, but in fact you could make very broad assumptions and you get that the entropy of the liquid has to drop below the entropy of the solid. The entropy in the solid is basically the spin entropy. The nuclear spins in the solid can point either up or down. If you have a mole of these things, that's R log 2 of entropy. And so that's this line up here. And actually, Pomeranchuk felt that the nuclear spin ordering in the solid will only occur at 1/10 millionth of a degree due to magnetic interactions. I'll talk maybe a little bit about that later if that's not the case. So anyway, no one felt that this would work. The idea was that the latent heat of solidification was negative. So to solidify helium-3 at constant temperature, you had to add heat to the system. If you didn't, in fact, the liquid, the solid would rob entropy from the liquid and the liquid would cool. This sounds very bizarre, but in fact it all actually works. No one tried it though because the work that you have to do, the P delta V work in order to solidify it, vastly exceeded this negative latent heat, and no one thought this was going to work. But eventually in 1965, a fellow named Manufri, a graduate student of Peter Kapitz's, tried this, and he started at about 100 milledegrees, and then the melting curve actually has a negative slope below where these two cross. And so he went, as he compressed, he went to higher and higher pressures, eventually came off the melting curve at about 20 milledegrees. That was actually not as cold as I could get with my dilution refrigerator, but David Lee, my thesis advisor, felt, in fact, that if you started with liquid here, that in principle you should be able to form solid deep into the nuclear spin ordered state, whatever that temperature was. And so this is what we were all after, at least what I was after. So this is the cell that I designed. This is the helium-3, and to decrease the volume, we pushed a metal bellows, this is beryllium copper bellows, into this region using a larger bellows, pressurized superfluid helium-4. And so this is a very simple thing. I should tell you that the design of this thing came together while I was laying in the hospital bed recovering from knee surgery following a skiing accident. So this coming June, I'm having my right knee replaced. But the fact that I had this unfortunate accident, in fact, allowed me to make an apparatus. Dave Lee, my thesis advisor, wanted to do this very differently than I did. Well, okay, so this is important. Now, this is obviously me. Well, I don't know if it's obvious. And this is my wife, Liu Shijiang. We got married at the end of our 3rd year of graduate study. And the reason I put this up here is that who you marry has a lot to do with what you end up doing with your life. And it's true for both men and women, I think. The guy that I apprenticed under at Cornell, my second year of graduate study, was married, and he and his wife had 2 kids. And his wife, who was a homemaker, she wasn't research anything. She had no career of her own. She could not wait to get out of fertility flats, that is, married graduate student housing. And so this particular graduate student that I mentored under actually wrote his PhD thesis, leaving blank spaces for the numbers. Now that absolutely ensured that he was not going to discover anything. I mean, I've asked him about that, he agrees. So I happened to marry someone who was very passionate about her own career. And so, in fact, you know, it was great. We would get in at noon, knock off for dinner together, work until midnight, then I'd take her home, go back to the lab. She would put her hair up in curlers, but she didn't like to use a dryer. So then that took several hours. I would go back home, which is an apartment, of course, at 4 in the morning, and we would go to bed. Those night hours were just so much more productive than the day hours were. It was absolutely amazing. Anyway, I'm sorry she's not here now, but she does not adjust well to jet lag. Anyway, so my 4th year of graduate study, so Liu Shijiang, my wife, took a postdoc, and that gave me 2 years. Oh, she got her PhD after 3 years. I had no idea what my PhD would be at that point after 3 years. And so my fourth year, she was in a first of a 2-year postdoc. There was a guy named Tony Leggett had made a strange prediction about spin diffusion in liquid helium-3 at very low temperatures. And so the idea was that the rate of spin diffusion basically is how far, if you tip a spin, how far it can precess before it loses coherence with all the precessing spins. And so there are 3 curves here which are for different magnetic fields, but you can't tell which curve goes with which color of dots there that scatters too high. So then we actually used my Pomeranchuk cell, and we got that. And now it's very clear. These are the theory lines, and they agree very well with the prediction of Leggett and Rice. And this, you'll see this was important later because Tony Leggett was the one that got the Nobel Prize for explaining what it was that I discovered. So going into my 5th year of graduate study, this is my last year because my wife was in the 2nd year of a 2-year postdoc. I had no idea what I was going to do. I asked Dave Lee, and he said, just measure some property of solid helium-3 through its nuclear spin ordering transition. Well, no one had ever observed that transition. No one knew what the temperature was. We thought it was 2 milledegrees. It turns out it was almost a factor of 3 lower in temperature than that. And no one had a thermometer that would stay in thermal equilibrium with the helium-3 down to those very low temperatures. So I really didn't know what I should do. And I just until, I guess, later that summer, Dave Lee got a preprint from John Wheatley, this famous person who had cooled helium-3 down to 2 milledegrees. And they were looking at how the melting pressure shifted as they applied a magnetic field. And what they found, this is the theory line here, and they got shifts which were huge by comparison to that theory line. And so first thing I did, of course, you always want to go in and reproduce the other person's results. And when I tried to do that, this is my data, and it was consistent with this theory line, but there was some scatter, about 0.5% in the temperature. And so I kept trying to get better quality data, and eventually 2 other members of the group, a graduate student and postdoc, went to David Lee and Bob Richardson to complain that I was monopolizing the lab's only NMR magnet. I'd done so for 3 months, and it was time that I give it up. And so Dave Lee and Bob Richardson agreed, and for that, they shared the Nobel Prize. Now, don't take that at face value. If in fact they didn't take the magnet away from me, I would have never done the experiment that led to the discovery of superfluidity in helium-3. So what happened was that I decided I would keep my apparatus cold because when they cooled their apparatus down, something might go wrong. But then, since I had to keep putting liquid nitrogen, liquid helium in it, I decided that I should try to do something. So I said, okay, we've measured the melting pressure as a function of temperature down to 2.7 milledegrees. Below that, I can just extrapolate. And so the idea was to start converting liquid helium-3 to solid at a very constant rate and just see what the temperature does. So this is the melting pressure, which is essentially my thermometer. We'd started at 22 milledegrees, and then here I rebalance the bridge that measures the pressure, and it continues to cool. And then at this point that I've later labeled as A, there was a very sharp decrease in cooling. And I looked at that and I said, oh, it's terrible. And I don't want to see that. And I assumed that what happened was the metal bellows had started pushing on solid helium-3, and that would cause irreversible heating. So this was the day before Thanksgiving, and so I terminated this run, and I let the dilution refrigerator pre-cool this thing down to 15 milledegrees, and I tried this again on Monday after Thanksgiving, and so here we are. It should have been flat across, and it looked rather badly distorted. Here it is again, going the other direction. So this is low frequency to high frequency to low frequency. Then I go through this B transition, the lower temperature of these 2 transitions, and what I found was the liquid signal dropped by a factor of 2. Well, the solid signal actually dropped too, but by about 1%. And so I said, it's very clear that this transition is in the liquid. And if you imagine forming Cooper pairs, one with a spin up and one with a spin down, this would not contribute to the NMR signal. And so I wrote in my lab book, 2:40 in the morning. This is such a wonderful time. No one's bothering you. You can think about what you're doing. Have discovered the BCS transition in liquid helium-3 tonight. And then I explain what I tell you. I will make a long story short. I was the only person in the entire physics building that night. I wanted to share this good news with someone. And eventually at 4 in the morning, I called up my thesis advisor, Dave Lee. And you have to be pretty sure before you do that. Dave Lee agreed that this must be good. Dave did not get any more sleep that night either, by the way. I didn't get any sleep that night. By the way, this 2:40 in the morning, the phone call I got from Stockholm, 2:30 in the morning. But I was, of course, a different time zone. So anyway, so then eventually we went back and looked at this A phase. The idea was we thought that transition was in the solid. So this little red line is what the all liquid signal looks like. And just above the temperature of the A transition, we had this huge thing. This is mainly solid helium-3. The question is, would that shift to higher frequencies as we went through the A transition? What we found was the solid didn't shift, but the liquid shifted. And it shifted to higher and higher and higher frequencies until we saw that little drop in pressure, which signaled the B transition. Then this thing disappeared. Clearly, both of these transitions were in the liquid. And we looked at this in magnetic fields, and if you plotted the liquid frequency squared minus the solid frequency squared, all of the data over a factor of 20 in magnetic field, difference in magnetic field, collapsed to a single line. So we wrote this up, and I sent a preprint to Tony Leggett, who was this guy that had predicted this effect of Leggett and Rice. Who would have ever expected that the liquid's frequency could shift? In fact, the paper that we submitted to PhysRev Letters was rejected because evidently the reviewer didn't think we understood how to do nuclear magnetic resonance. So if you've ever had a paper rejected by PhysRev Letters, you're in good company. Anyway, so let me just talk a little bit about these strategies. Again, utilize new technologies to view nature in a new perspective or from a new perspective or in a different realm. New perspective usually means higher resolution or something like that, or adding a magnetic field or something. Don't give up when things are going bad. When they took the magnet away from me, it would have been a wonderful time. I was bitterly disappointed with what I was getting. Warm up and go for a weekend camping in the Adirondack Mountains, but instead I stayed on, and in fact, I made a major discovery in science. Spend a little bit of time doing something different. Curiosity-driven research is fun, and it can be rewarding. And nowadays, when instrumentation costs so much money, you have to propose something very specific to get the money to buy all that stuff. Do something else with it. I think it's really good advice. And if you're a graduate student, my strong advice is avoid too many commitments. Now, my wife is Chinese, and she'd wanted me to learn Chinese. Cornell was offering in the fall of 1971 a course in conversational Chinese. And so we'd sort of agreed that I would take that course so I could finally learn Chinese. I didn't learn it from her. Just a few insults like "ni zhou meng," which means you're dreaming. You're dreaming, or "xiao se wa la," I laughed myself to death. Anyway, then eventually I said, wait a minute, this is my last year of graduate study. It's my last chance to do something that proves that I can be a physicist. I don't need any additional commitments. And I would guess if I had taken that Chinese course, when they took the magnet away from me, I would have been so far behind in learning Chinese, I would not have done the experiments that led to the discovery. Okay, avoid too many commitments. And I didn't tell you, but when I went to Michael Fisher, the reason I did that was because, in fact, a squirrel was running along the power lines that brought power into Cornell University. And somehow he tried to jump across one of these insulators, but grounded the whole power system. And his carbonized body brought down the entire power grid at Cornell. that basically caused all the pumps stopped, and one of them leaked air back, and I got an air block inside a pumping line inside my cryostat. So I had to warm up. When I cooled back down, I had a leak in my cryostat. This basically gave me a month to think about how to resolve this question about whether these transitions were in the liquid and the solid. So back off from what you're doing occasionally to gain a better perspective on the task at hand. Very, very good advice. We become myopic when we focus too tightly on our work. Okay, we're just about done. Okay, here I am getting the Nobel Prize. This business, by the way, your right hand goes underneath the king's left hand as he gives you, I mean, we practice this, not with the king, but with a stand-in for the king. Okay, here's Tony Leggett. So it's 96 to 2003. So I guess 8 years later, he got his own Nobel Prize, which he shared with 2 Russians for their work on superconductivity. But basically, this is all BCS physics.
Tony missed your right-hand pull-up there.
Did he? My God. Maybe it's because I'm left-handed. No? Well, the king seems to have found his hand. I'll ask Tony about that. Okay, now the last thing I want to do, this is my cell again, and I put next to it the names of people that contributed technologies such as nuclear magnetic resonance, the pressure transducer, the helium-3 itself, Ed Hamill, the helium-3, helium-4 dilution refrigerator, Ed Edwards and Hall, Bardeen, Cooper, and Tree for their theories, the modification of that to helium-3 by Phil Anderson and a number of other people, Pomeranchuk's prediction of the refrigeration technology I used. Without any one of these, I would guess that I would not have made the discovery that I made. So my last message to you is advances in science are seldom made by individuals alone. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support scientific research broadly, even in India, and encourage scientists, oh, that wasn't there, okay. Encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are made. Thank you. Does anyone have a couple of questions? Yes?
In the 19th century, Hadamard wrote a book on the logic of scientific discovery, which you may be aware of, and what he did was to ask 100 colleagues in Europe as to how they had made their major discoveries. And 30 of them said that it was not that they were deliberately thinking about their problem. It was some kind of a coincidence which gave them the vital clue which led them to their discovery. Now, does your own discovery have a coincidence angle to it, is my question.
Well, we were, of course, thought I was studying solid helium-3, but because of the cooling technique, I just was lucky for me. I had liquid and solid helium-3 coexisting inside the cell. So that's really what came together that allowed that discovery to be made. And by the way, the transition temperature that I measured was 2.6 millidegrees. That was higher than the temperature that John Wheatley had gone to. It turns out that the transition temperature is fairly strongly pressure dependent. So Wheatley was operating at saturated vapor pressures where the transition temperature is actually 9/10 thousandths of a degree because he could cool his sample colder. But if he had worked at higher pressures, he would have made the discovery. So, I mean, this whole business of how discoveries are made, and I find it remarkable that you, after having so much fun, I mean, I would say that I made 4 significant discoveries in my career, and every one of them is exciting, although only one of them has won any prizes. But after having so much fun, I think they surely shouldn't reward you with a Nobel Prize. They should give it to some poor guy who's worked very hard and nothing has ever come out. Yes?
You mentioned about the importance of family support in pursuit of science. Could we ask a similar question for the society as well? So perhaps a question could be formulated as that certain types of societies are more likely to contribute to the advancement of science. So maybe I could make it more specific. We could take society A, which is, let's say, less open, where openness could be defined in terms of less freedom of speech, or maybe the society takes it upon itself what to wear, what to dress, what to eat, what to drink. And there's another society, society B, which is less intrusive and which lets you be what you are, subject to certain social order. And if we have to make apples to apples comparison, then maybe, let's say, both society A and society B have access to modern education. So could we make a statement that society B is more likely to contribute to the advancement of science?
It's kind of interesting. I guess to some level, I'm sure you're correct. But my personal feeling is a far larger influence on what people do, and particularly whether they go into science or not, is their experiences as young children. And certainly in the United States now, I mean, the K through 6 teachers don't know any science, but they know very well how to turn off questions from their students regarding science. It's very sad, and I think it's troubling as well. So, you know, I think that what you've talked about is, of course, a big problem, and it's very difficult to change a society in order to get more research going on. But surely the idea of fascinating children with physical behavior at a young age is not that hard to do. Certainly what I've been pushing for, but not, you know, very effectively, is that in elementary schools, each elementary school have a science teacher. And that person would go around, because at least in the United States, in elementary school, the kids are always in the same classroom all day, every day. But that teacher then would go around those classrooms and do some demonstrations. And it's so easy to get kids hooked. I mean, one time I went in and gave a talk to the entire 6th grade class at Plainfield Elementary School, and I had liquid oxygen, which I picked up with a magnet, and of course liquid nitrogen, and I would have a coil of wire which I would trick kids into attaching the leads, which were bare, to a battery. When they removed the leads, they got a shock. Little kids love to get shocked. I actually discovered Faraday's law when I was 10 years old, packaged this, took it to school, and was shocking all of the classmates. They knew they were going to get shocked, of course. You do that today, and you end up in Guantanamo Bay, is my guess. So talk about a free society. We think of our society as being very free, but I don't. I mean, laws do a lot. And I must say, in the United States right now, the fear of lawsuits really dictates a lot how things are done. Certainly in medicine, but I think in a lot of other areas as well. I was doing this with a lady from the NSF, and she absolutely did not want me to shock the students, because she was afraid the NSF would of course get the blame if the kid had a heart attack or something like that. Well, I've shocked myself lots of times. Anyway. Any more questions?